This video is going to cover the mathematics that is generally found in the MCAT. My name is Dr. Adam Daly, and I work with students in the chemistry and physics section of the MCAT. Okay, so the first content I'd like to review are the prefixes used in the SI system and some general applications of conversion factors. So there are going to be many units given that are not going to be in standard unit. They're going to have some prefix associated with them. Like for example, 100 centimeters. Right? Now we can't really do any calculations with 100 centimeters. That would be located here. So what we want to do is convert that into meters. Well, we're given the factor 10 to the minus 2. And so what we're going to do is the quick way, because we're doing this fairly quickly, we're not getting any type of partial credit for showing our work, is that we can replace C with 10 to the minus 2. So this just equals 100 times 10 to the minus 2 meters. Times 10 to the minus 2. So this portion, the times 10 to the minus 2, is just replacing C. Now, of course, we could do the entire conversion factor. It says for every 1 meter, well, there's 10 to the minus 2 meters for every 1 centimeter, right? That's how we would read the factor. And we would get 100 times 10 to the minus 2 meters. Right, now we have scientific notation, so we can use this as 100 times 10 to the minus 2, or we can move the decimal. So what we're going to do is we have 1, 2, and when you move to the left, that's a positive change in the exponent. So that means this would be the same as going 1 times 10 to the plus 2 minus 2, or 1 meter. Right, so by moving over to, but oftentimes when we're doing calculations, as you'll see later in the video, we're really not even going to change this number, right? The number in the significant in scientific notation is called the significant. And so the significant, that portion of the number that's times 10 to the, we're usually not going to change that. It's not really in our best interest to change it, as you'll see in some examples. But there are others that are really useful. Um, Kilo, right? So kilo is really important. And we see that in kilometer. That there's 1,000 for every 1,000 meters, there's 1 kilometer. And then, but the most use for these prefixes on the MCAT that I've seen are the small values, right? The small prefixes. So centa, millimeter, 10 to the minus 3 meters. The 10 to the minus 3 meters, and then we have the micron or micrometer. That's 10 to the minus 6 meters. This is the micron or micro, and the Greek letter mu. Then we have nanometer, 10 to the minus 9 meters. And so for example, visible light and UV light. So UV light and visible light span 100 nanometers to 700 nanometers. So if we wanted to convert that into meters, then we would just use this factor for the n. So 100 times 10 to the minus 9 meters to 700 times 10 to the minus 9 meters, right? And so we're just taking this factor and replacing the n for it. And that's usually very handy when we're working with scientific notation. Okay, so then it's going to be right. The next aspect of mathematics that's really important to feel comfortable with is the use of logarithms and exponentials. And, like for example, for the sound level, I'm going to say like we should be able to do is solve for any. So if we look at the sound level equation, beta is 10 log I over I0. And if we want to solve, so we want to do solve for I. So the goal is to solve for I. And the first thing we want to do is we want to clear every constant from one side of the equation that has the logarithm. So we go beta divided by 10 equals log I over I0. Okay, now let's keep in mind that this is log base 10. Log base 10. And so from now is say, well, how do we solve for I? And what we're going to take advantage of is that if we have log of x equals 5, and what is x, then what we could do is go 10, 10, to the log x equals x equals 10 to the 5. So this is a very useful expression, right? 10 to the log x. So anytime we want to clear a logarithm, we always raise both sides of the equation to the power of 10. And so in this case, what we're going to do in our sound level example is now we're going to just do is raise this to the power of 10 and this side to the power of 10. And then we get 10 beta divided by 10 equals I over I0. Right? And so now we can solve for I. So I is going to be I0, 10 to the beta over 10. And we've seen questions like this in different forms, which is, beta for a hockey game, let's say, could be 90 dB. This is for the hockey. And beta for lawnmower. I just want to know, what is the ratio of eyes for the hockey versus the lawnmower? Lawnmower. Okay, well, then we can use this equation. We can say, okay, for I over hockey over I of lawnmower equals 10 to the 90 over 10 divided by 10 over the 70 over 10, which is 10 ninths over 10 7, which is 10 9 minus 7, or 10 to the 2. So it's 100 times, right? So it's 100 times more intense sound in the hockey game than being near a lawnmower. And that's how we would use that, the power first determining I and then solving for it. Right. We have some other examples up here. So let's take it. Let's try that. Some other examples here are, let's use the natural logarithm. So the natural logarithm is for n exponential decay. So for n equals n0, e to the minus lambda t, solve for t. Okay, so this is going to be pretty handy. So what we do the same thing we did before with logarithms. We have to take all our constants and put it on one side. But now, because we have the natural logarithm base e, we use natural logarithms. And for that, we are going to have, for example, e to the x equals 5. And now the question is, how do we get to this result? Well, we take the ln on both sides. And by taking the ln of both sides, so the ln of e to the x equals x. So anytime you take the logarithm, you automatically get the exponent. And now we see x is equal to ln of 5. And that's what we want to do here. Here we want to take the ln of both sides. Take the ln of both sides, and then what we get is the ln of n over n0. See if I can make that thicker. Oops, kind of get rid of it here. So the ln of n over n0 equals, and now we're just going to have minus lambda t. Okay. And this, you see this often in what are called half-life equations. Half-life equations, which is, that is where n equals 1/2 of your original concentration or your initial amount of particles, usually nuclear or with concentrations. And so that would be the ln of n0 over 2 divided by n0, which equals the ln of 1/2, which equals minus lambda t, or that t is equal to the ln of 1/2 over lambda, the minus sign. Okay, so being able to work with the natural logarithm and the logarithm are very useful. Okay, I think that is, let's take a look at the pH real quick while we're here. Okay, Okay, so here we have the pH is equal to minus. Here we have the pH is equal to minus log of H plus, right? So there's a couple things. So if pH equals 5, what is the concentration of H plus, right? That's the type of problem you might see. So in this case, we'd say, okay, well, we're going to take them. So minus pH equals log of H plus. Oh my goodness. I'll have to go a little bit farther down here. So the minus pH is equal to the log of H plus. So you want your logarithm completely on one side. You raise it to the 10 power, both of them. And so we get 10 to the minus 5 equals H plus. So those are very handy tools with logarithms, how to solve for a number and how to um, uh, get access to an exponent. If we look at the Henderson-Hasselbalch equation here, oftentimes you'll have to be able to estimate a log value itself. So let's take a look at that. So so for example, if you have the log of a minus over HA, and you're told that this is log of 10 to the minus 2 over 10 to the minus 4. And now what is that? Well, that is the log of 10 to the minus 2 plus 4, or log of base of 10, 2. Okay, so we want to know what is that number. And so it turns out that logarithms in scientific notation go very well together. So the log is always going to be your exponent value. So the log of 1 times 10 to the 2 is equal to 2. The logarithm of 3 times 10 to the minus 9 is approximately the same as the log of 1 times 10 to the minus 9, and that is going to be approximately equal to minus 9. Right, so you always try to get everything into the exponent of a in scientific notation if you're going to have to take a logarithm, because you want to be able to extract out the exponent. All right, so let's move on. Right, so let's take a look at doing problems. So here is a problem from the MCAT prep, and it's going to give us a lot of practice in what you're going to be what you're expected to be able to do using the techniques that we just described. All right, so we want to determine determine the current in the circuit if the circuit is charged, right, for 1 millisecond. And so anytime we have current, right, so this is a physics question, and not that this is a physics video, but in general, so you see you have an equation, you're going, okay, current is a lot of things. It's like V over R. It's also equal to total charge. Total charge over, oh, sorry about that, total charge over time. And Well, we need charge, and so what we see in this problem is we have a capacitor. And the charge of a capacitor is the relationship we have is QVC. So charge equals voltage times the capacitance. And so if we want to calculate the current, then we're just going to divide this by time and we get current, right? So that's the equation. And worked with lots of students on problems like this, and you have the right equation. And now what we want to know is, how do we get the current? Put these numbers in. So we see we have 3,000 volts. We have a capacitance of 25 microfarads, and we have 1 millisecond. So what we want to do is be able to combine all these numbers into a formula. Well, the volts is 3,000 volts. And then we have, and which I'm going to put immediately into scientific notation. We have coulombs, which is given as 25 right? Microfarads, which I'm going to put in scientific notation, 25 times 10 to the minus 6 farads. Okay, I'm not going to change that. I'm just going to take my micro, which I know is 10 to the minus 6, and just substitute for it. I'm going to leave 25 as it is. I don't want to move it around. Just want to leave it like that. And what else do we have? We also have time, right? So time is equal to 1 millisecond, which is the same as 1 times 10 to the minus 3 seconds. So you can see we're getting a lot of interest, right? In milli, 10 to the minus 3, micro, 10 to the minus 6. And just for 10 to the minus 9 would be nano. But you can see that there's going to be many opportunities to use these conversion factors. Right, with that, what we can do is plug it into the formula. So we have 3 times 10 to the 3 times 25 times 10 to the minus 6, all divided by 1 times 10 to the minus 3, right? So those are going to be our formulas. Now, one thing we're going to do is we're going to deal with the numbers in the boxes first, right? So this is going to be 3 times 25 over 1. And then we're going to do our 10 powers of 10. So this is 3 minus 6 plus 3, right? So if you have a minus 3 in the denominator, it turns into plus 3 in our scientific notations, like dividing by a smaller number. And now when we want to compute this, what we see is we have 3 times 25, so we have 75, 75 times 10 to the 6 minus 6, which is 0, or 75 amps. Right, so 75 amps from doing the problem. When you discharge this capacitor, 25 microfarad capacitor at 3,000 volts for 1 millisecond. Okay, and so it's really important to feel comfortable with the numbers, because many of us feel that, getting the formula is all right. I have the formula, or you're giving it to you in the passage. And the last thing you want to do is mishandle the calculation. All right, let's take a look at another example. So another example that has a lot of exponents and that are pretty notorious for in the MCAT are light calculations. So when we look at the light calculations here, we have this passage and there's a lot of information in here, but we sort of kind of boils down to is this question, which has nothing to do with the passage. And so in the chemistry and physics, we often recommend students don't start with the passage, and you just start with the question. And we look at this question, we see that we have uh, a wavelength. This is the 656, right? 656 nanometers, which we're just going to write out. We're just going to write the 10 to the minus 9 here, substituting for n for nano, we're substituting in the 10 to the minus 9, right? There's no conversion factor, it's just direct replacement. And we're asked, what is the frequency? Okay, so the frequency, we have lambda, oops. So we have lambda times the frequency equals the speed of light, right? That's the equation that we're expected to use, and where c is given in the passage, 3 times 10 to the 8 meters per second. All right, so frequency would be 3, 3 times 10 to the 8 meters per second, pretty big number, divided by 656 times 10 to the minus 9 meters. All right, so, but we're not really that interested in the 56. So what we're going to do is we're just going to change this to 3 times 10 to the 8 divided by 600 minus 9. Right? That's what we really want. Why? Because now what we have are two numbers here that are really easy to work with. We have 3 over 600, which is 1 over 200, times 10 to the 8 minus a minus 9. So now what we have is 1 over 200, or so 1 half, times 10 to the minus 2 times 10 to the 17, which is equal to around 0.5 times 10 to the 15, or 5 times 10 to the 14. So let's take a look at the possible solutions here. Now, initially, we could remove these two. Frequencies of light are high, right? They're very high. And so there, we don't have any frequencies that are negative. Now, these values might be these values might be something that you might see for energy, 10 to the minus 14, 10 to the minus 16, but frequencies are big. So we can just kind of get rid of B and D right off the bat. And then the question is, well, is it 4.6 times 10 to the 14, or is it 2.1 times 10 to the 15, right? Those are the only choices we have. Now, the first thing we could see is there's no way to get 2 here if we're taking 3 and dividing it by a number like 6. And so we could have stopped, right? For C, we could have stopped right there. Frequency is 3 times 10 to something over 6 times. Okay, so we already getting right there. We know this is 0.5. So from there, we could have stopped doing the calculation. We don't even need to know the exponents. So if we were going really fast in this type of problem, we could distinguish A and C right away from this ratio. But of course, we could do all the steps. And if we do all the steps, they're over here. We get about 5 times 10 to the 14. That's about what this answer is. Even though we did some rounding, it gave us generally the correct answer. And you want to put the numbers that are most favorable for you. You know, 656, nobody cares. It's 600. Okay, move on. All right, so here's another problem. This is taken from another practice exam, the Atwood machine. And so this has a fairly long analysis to it, which I'm going to suggest you don't need. So let's take a look at this problem. This problem is about competing masses, and we want to know the general expression for the acceleration. So do we expect this to accelerate? And the answer is yes, we expect this system to accelerate that way. And so what's good to do in this problem is just kind of look at the extremes. 5 and 5, no acceleration. G. Okay, so if there's no mass over here, right, you're just holding this with your hand, right? There's your hand and you let it go. We know that's going to come down. The acceleration equals G. If you put equal masses, then the acceleration is 0. All right, so it must be that when we subtract these, right? So we're subtracting. So 5 and 2. So subtracting them would give us 3, right? 3. And that's what we have here, 3g, 3, but it's not 3g like it's 3 times the acceleration of gravity. It's 3/7, which is the sum, which you kind of get from the entire solution. But what we can see here is we can exclude the 5/7 and 2/7 and g because they don't really have the form we need. We need something that's a competition. If the masses are the same, it's 0. It doesn't make sense that it would be only mass 1. It doesn't make sense that it would only be mass 2, but it does make sense that it's mass 1 minus mass 2 because that's what contributes to the acceleration. So problems like this, even though if you can't think of the entire solution here, the working it out in terms of, well, what is a good idea even without doing a lot of math. Okay, so with that, I would like to say that that's a review of the prefixes and logarithms, their applications and strategies for working on problems, and I hope you found this to be useful.